Hey y'all, today we're going to take a look at resonance. Now in the last video we looked at formal charge and how to calculate it and how to use it to pick the best option for a Lewis structure. And today what we're going to do is we're going to apply formal charge in a slightly different way, and it's going to be in the way of determining when there will be resonance. And we also sometimes refer to this as resonance stabilization within a compound. So let's take a look at this. We're going to build out some compounds and we're going to talk about where resonance comes in, how it's going to affect the compound, and what it means for the overall position and location of different electrons. So we're going to start with a compound that's pretty commonly used in resonance examples, and that's ozone. Ozone is O3. You might have heard of ozone. It's part of what makes up the ozone layer. It's a very reactive compound, and let's talk about how we would diagram it. We're going to do it the same way we did for any other Lewis structure. So go ahead and draw for me the structure for ozone now, and then come back when you've done it, and we'll go from there. If you look at the structure of ozone as I've drawn it, you can see that we wouldn't be done yet. The central oxygen doesn't have enough electrons. It only has 6, 2 in each of the 2 covalent bonds, the single bonds, and 2 in the lone pair. That's 6 electrons. Now, that's not okay. Oxygen in the center does need another 2 electrons. But if you look at this, you don't necessarily have any way to know whether you're going to take those 2 from the left oxygen or the right oxygen. Now that's a first big clue that resonance is going to be in play here. Because you're as likely to get those 2 electrons from the oxygen on the left as you are from the oxygen on the right, we're going to end up seeing both effectively happen. So what does that mean? Well, it means that both structures are kind of going to exist halfway. Let me show you. So if you take a look at these 2 Lewis structures, you'll see that they're essentially mirror images of each other. In the one on the left oxygen is double bound to the central oxygen. On the one on the right oxygen is double bound to the central oxygen. This structure, realized I forgot my lone pair on the central oxygen there. This structure shows resonance. The double arrow in between the 2 structures tells you that it is going to show or exhibit both simultaneously, but at the same time, neither one completely. The reason for this is called delocalization of electrons. Electrons are going to be moving. Remember, electrons exist around these atoms in the form of a cloud. It's not like electrons are just sitting there in the form of these bonds. Instead, what's going to happen is electrons are going to end up averaging between the 2, essentially single and a half bonds, or 1.5 bonds. So instead of a single bond or a double bond, each of the 2 bonds that you're going to see in ozone between the oxygens is actually going to be identical. And it's going to be the same as what you would consider to be like a 1.5 bond. And the reason for this is because resonance is going to overall create a structure that is the average. Okay. So what does this mean for formal charge? I mentioned how formal charge plays a role. So let's take a look at formal charge in each each of the 2 options. I'm going to call the oxygens 1, 2, and 3 based on them being on the left, the middle, and on the right. So the oxygen on the left has a formal charge of 0, the middle oxygen has a formal charge of +1, and the oxygen on the right has a formal charge of -1. Now, if we look at the compound on the right, in the way that it is arranged, now you can see that the oxygen on the left has a formal charge of -1. The central atom still has a formal charge of +1, and the one on the right now has a formal charge of 0. So why is this more stable? Well, because if we average the formal charges, all right, across the compound, the left oxygen has an average formal charge of -1/2, which is better than -1. The formal charge of the oxygen on the right also has a formal charge average of -1/2, which is better than -1. And the formal charge of the middle one is, in both cases, +1. So that's going to be the same. But here's the thing about formal charge. It's not a linear effect. Going from a -1 to a 1/2, -1/2, is a much bigger difference than going from 0 to -1/2. So in the end, averaging a lower value, in this case of -1/2 for each of the two oxygens on the sides, is going to be better than one of them being 0 and one of them being -1. This is called resonance stabilization for a reason. It creates a more stable compound in the end. So when we're looking at resonance, it is predicated on formal charge minimization. So you want to minimize the formal charge, get them as close to 0 as possible. And we do this by delocalizing electrons. And I say we do this, but really what it is it's just the most stable way for the molecule to be formed. And therefore, this is the structure that the molecule will show. You're going to be expected to show resonance using these double arrows. You won't necessarily have to calculate or show formal charge each time, but it is really important to recognize when when resonance will exist. And like I said, the big clue here is because you won't know where the double bond or the triple bond in some cases is going to come from. If you have options, then it's most likely going to be all of them in the form of resonance. Let's take a look at another example now. In nitrate, we have now a charge. Remember, the sum of formal charges add up to the total charge of the compound. So let's draw nitrate real quick. Again, I want you to take a second to draw it. Come back when you're done and we'll go through it. Now, nitrate has 24 electrons total where you need to account for. In this case, if you take a look, we've got around each oxygen 8, all right? 2 in each bond, 6 in the lone pairs. So 8 times 3 is going to therefore be the 24. So we've got 24 electrons. But as you can tell, the nitrogen is not filled in terms of its valence shell. It has 6, it needs 8. So where do we get that extra pair of electrons from? Answer is from one of the oxygens. But which one? Well, that's kind of the key. We don't know which one, but it can be all of them. Because they're each as likely to give up those electrons as the other, we create resonance. So in the first one, I'm going to do the top left electron, or the top left oxygen. But then I'm going to have to redraw this same structure 2 more times, where each of the other oxygens is going to be the one double bound. Also remember, even in resonance, we have to account for charge. Okay, so each of these three structures in the end is correct, but none of them will be correct in terms of them alone, because really it's an average across all three. So if we look at all three and just look at the formal charges, what I'm going to do is I'm going to put the formal charges for each atom on top. So I want you to calculate the formal charges for each atom, each oxygen atom, and the nitrogen atom in each of the three compounds. Go ahead and do that now. So, a couple things to note. Number one, I'm never going to show these as actual charges on the Lewis structure. These are not real charges, right? Not like the charge in the top left or top right corner there outside of the brackets. These are formal charges. I want to make sure that you don't actually show these on any Lewis structures you're going to draw. But I wanted to do this for sake of speed and also for sake of not polluting my paper with too many numbers and words and letters. So if we look at this, the top left oxygen will have an average formal charge of -2/3. The top right oxygen will also have an average formal charge of -2/3, and the bottom oxygen will also have a formal charge average of -2/3. The nitrogen's always going to be +1, but it's the least electronegative atom, so if anyone's going to have the positive formal charge, that's the one to do it. Okay? This resonance structure, again, is going to result in an average of, instead of a single bond for two of the oxygens and a double for the other, all three oxygens are going to have equal bonds, which are going to be about 1.33, like 1 1/3, okay? Because the average bond order for each of the three is about 1 1/3, okay? So what you can do for resonance is not just calculate the number of the formal charge, but also understand bond order, right? Single bonds and double bonds and triple bonds, right? We all understand those as 1, 2, and 3, but there are bond orders that are somewhere in between, and that can be created through resonance in this case. All right, here's your challenge. Now we're going to do carbonate, CO3 2-. I want you to do this one on your own completely from the beginning, all right? All the way to the end, and then at the end, we'll talk about it, all right? So go ahead and pause the video, do carbonate, CO3 2-, all right? And then when we get back, we'll talk through it. Okay, so carbonate looks like this. 3 possible resonance structures, each of which is going to end up with a double arrow between them, total charge of -2 in the top corner. Remember, resonance comes down to, can you identify when it's going to happen? And when it's going to happen is always going to be predicated on, is there more than one option for where the double bonds could form? In this case, the answer is yes. Therefore, resonance will form. Each of the oxygens will be bound to carbon on average 1 1/3 times. So in other words, the bond order would be 1 1/3 for each oxygen-carbon bond. In other words, all 3 bonds are effectively the same. Okay? So that wraps up today's video. Today we learned about resonance, how we draw resonance structures in Lewis diagrams, but also how we identify when resonance will occur, and most importantly, and this is a really big deal, what it means for the structures themselves. Remember, resonance is about reducing formal charge and making a more stable structure overall. I hope you enjoyed the video, and I'll see you in the next one.